we can start. So it is a pleasure to have with us today Dr. Oliver Just. He is coming from Germany, from the Helmholtz Center for Heavy Ion Research. This is located in Darmstadt, in Germany. He got his PhD in 2012 at Max Planck for Astrophysics in Garching, in Munich. And he was there also postdoc until 2017. Then he got a special postdoctoral fellowship at Riken, Tokyo, until 2020. And then he's at the institute he's located today. You have got already the announcement. You see the title on the screen, what we can learn from kilonovae about nucleosynthesis and high density matter. And we're ready to, and very curious to listen to your talk, Oliver Just. So please, you can start.
Thank you very much. Thank you. And thanks for the invitation for the seminar talk. And I'm very happy to present our work here of our recent years that we have, and our results that we have gained with mainly in collaboration. So the results that I show will be mainly done and obtained in collaboration with this synergy grant that we have gotten in the recent years. It's called HeavyMetal Synergy Grant. Here at GSI, together with other nodes in Copenhagen and Dublin and Belfast. So I'm going to show mainly work from these collaborations here. And so our work is focused on kilonovae. Kilonovae are explosions, not like supernova explosions of single stars, single massive stars, but explosions of basically of a binary merger of neutron stars. So two neutron stars merge and collapse and create a huge energetic explosion, and this is called then a kilonova. And in fact, one can learn many interesting things connected to nucleosynthesis, to heavy element nucleosynthesis, but also learn things about the constituents of high density matter. Yeah, and this I will going to talk about today. And it will be relatively introductory, but if you have questions at any point, you can of course interrupt me. So what is the main one of the main motivations for us is basically the question, where does the heavy element repertoire that we see nowadays in the present universe come from? We know that hydrogen and lithium are produced very early after the Big Bang and Big Bang nucleosynthesis, in primordial nucleosynthesis. But basically all the heavier elements formed during the several generations of stars. And so if one plots now as a function of the mass number of elements, the mass fraction for different epochs of galactic enrichment, then one, as I said already, one starts with mainly hydrogen and helium and lithium. But then one also sees that stars are enriched with elements up to iron, but younger stars are also do not only contain iron but also heavier elements. And this is in fact quite mysterious why they form heavier elements, because if one looks now at the binding energy of this is a relatively ugly plot here. I just took one that I found here that just shows this relation here, which is the binding energy per nucleon as a function of mass number. Then we see that at iron we have a maximum. That means basically that due to equilibrium processes happening in stars, energy is only released for the fusion of up to iron, basically, but not heavier elements. So if you want to create heavier elements, then you need to input energy instead of gaining energy. So it will not be something that happens in some equilibrium thermodynamic process. It will happen, it will be connected to something that is that needs energy input, and particularly neutrons, because in order to create these heavy elements, one needs to start from more massive, from more lighter elements, and these elements then need to capture neutrons. Sorry. So basically, this is one of these main processes that creates heavier elements is this rapid neutron capture process. There are also other neutron capture processes, but the ones that really create the heaviest elements like gold and uranium is believed to be at least this rapid neutron capture process. Why is it called rapid? Because it is characterized by this behavior that neutrons are captured faster than these newly formed elements can decay, mainly via beta decay. So you capture neutrons basically up to the point of the neutron drip line. The neutron drip line is basically the demarcation line where you get nuclei that will not capture any more nucleons because they are not stable anymore. And you capture up to the drip line, and then these nuclei decay. And this is in contrast to, for example, the slow neutron capture process. The slow is taking place closer to the line of stability here. It's indicated here with this orange line in this nuclear chart. Nuclear chart plots the number of neutrons versus number of protons versus number of neutrons here. And all these black elements are stable elements here, and the S process is basically going along this line here. And in this case, the beta decay happens faster. The beta decay rates happen faster or are faster than the neutron capture rates. So that's the opposite scenario as for the R process. So the R process is what we are interested in. And one can see already, if one looks at the abundance of R process elements in the sun, for example, that is plotted here on the right, then one notices these characteristic peaks here: first peak, second peak, third peak, and these are basically connected to these magic neutron numbers 50, 82, and 126, which 82, 126, and 184. And these basically are relatively stable regions of the nuclear chart, where you create an accumulation. During this R process, you create an accumulation, so-called waiting point here, where the beta decay rates are relatively slow, and material does not decay very fast, and therefore you accumulate material during this R process. So this is from the nuclear physics point. So from the astrophysics point that we are mainly working on here, I am mainly working on, so to say. We also have collaborators here at GSI that work mainly on the nuclear physics. But I'm mainly working on the astrophysical modeling of sites that could allow for the R process. And for us, what is important mainly is to look into models that create a low value of this YE, of this critical quantity YE, that is a fraction of protons to nucleons, which is also the fractions of electrons and to nucleons. Therefore, it's called the electron fraction. And in order to get neutron-rich conditions, which you need for the neutron capture process, then you need a value lower than 0.5. So in the subsequent slides, you will often see this quantity YE. And in order to get viable R process conditions, then this number needs to be much lower than 0.5, basically, in order to create really the heavy R process elements. So far from the astrophysics point of view, historically, many sites have been suggested to be R process sites, beginning or mainly during the longest period of time. Probably the idea was dominating that core collapse supernovae are the main sites for R process nucleosynthesis. However, this has turned around more or less. So core collapse supernovae by now are not at all promising anymore, but at least not the ordinary types of core collapse supernovae, but more exotic types. For the example, the magnetorotational supernovae or collapsars are more favored, or the remnants of a magnetized supernova, namely magnetars, could erupt during magnetar giant flares. So these are suggested scenarios, basically. However, the only one that is really confirmed so far by observations is neutron-star mergers. Right, and this leads me to the next slide here. So basically, what is the idea here, or the the picture is that you enrich material here starting from a neutron-star merger. You enrich the interstellar medium with heavier elements. This interstellar medium is then the birthplace of new massive stars, and these explode then again, form new neutron stars, neutron star binaries, black holes, and these ones then merge again and enrich really the interstellar medium again. So it's a cycle basically of elements, and in each generation basically you more and more enrich the interstellar medium and the stars basically. And this is called then chemical enrichment or galactic chemical enrichment. Here I show a movie from an R process in action, basically. This was not from us, but from Jonas Lippuner at Los Alamos. We are performing similar simulations, but we didn't have such a nice movies. Therefore, I'm showing this movie right now here. And basically, so just for you to illustrate how this takes place. The time is here, so this is basically a process that happens on the time scale of several hundred milliseconds to 1 second. And on this time scale, you create all the heaviest elements already, which are far away from the valley of stability. And then on much longer time scales, these newly created elements decay. And this decay really takes place on minutes, hours, days, and weeks, and longer. And then you get this characteristic abundance pattern here, also first, second, third peak again. And this calculation here, this was just a sample calculation. So, and this heating, so this decay of newly processed elements causes energy generation, because radioactive decay produces energy, and this produces heat in the ejector. And you can calculate the energy generation from these decays. And because you have a chain of elements decaying on vastly different time scales, you do not have an exponential, like for a single decay. A single decay would give you an exponentially decaying energy generation rate. But for a chain of elements, you effectively get something that is close to a power law in the energy generation. So if you plot this energy generation rate versus time, 10 to minus 5 days is roughly 1 second here. Then after 1 second, more or less, you get a behavior that is close to a power law. And this power law goes roughly with T2 minus 1.3. And before the first observation of a neutron star, this was already predicted by also by a collaborator here from GSI, Gabriel Martinez Pinedo, and Brian Metzger in the US, that this characteristic or this energy generation could lead to observable electromagnetic counterpart or electromagnetic emission. And that is called the kilonova. Why was it called kilonova? Because it's roughly 1,000 times brighter than a nova. And so what happens there is basically you have this explosion taking place, and the ejected material expands with time. Initially, it's very dense. So that means that photons are basically trapped here, cannot leak out. But at some point here, this mean interaction, this mean scattering length between scattering and absorption and emissions of the photons here becomes comparable to the size of this ejector. And this is roughly the time when you expect the peak of this kilonova emission. And this was predicted to be, or this is known to be roughly then on scales of a few days to 2 weeks, basically. Yeah, this kilonova. So much longer than the actual R process. The R process was roughly 1 second. Kilonova takes place on a few days to weeks. Right, and the nice thing about this kilonova here is basically if we see such a kilonova with electromagnetic telescopes, then we can learn something about the R process, about mysterious process. And but in order really to understand this kilonova signal, what one also needs to understand is the interaction rates of photons with this newly created R-process material. That means you need to understand the opacities of photons in this R-process material. And the opacities in R-process matter are very complicated because they are mainly dominated by lanthanides, and lanthanides are very complex. These are basically the elements between the second and the third R-process peak. And when you create these, you have many valence electrons, and with these you can do bound emission and absorption. And they have many different energy levels, these lanthanides. So here we're talking about atomic physics, so not nuclear physics. These are really the atoms. So you have lanthanides that are recombined already, mostly recombined. They are singly or doubly ionized at the epoch of kilonova emission. And these valence electrons then can attain different energy levels. And the number of energy levels is very, very large. So this can be millions of different energy levels. This leads to more than many millions to billions of different lines that you can get. So interaction or emission lines and absorption lines. And this really faces or represents a challenge for atomic physics now, basically to calculate these lines and these opacities. And recently, a collaborator of us, Andreas Fleurs, has submitted, I don't know if it's published yet, a study on these opacities, where for the first time he not only predicted on a statistical level these opacities, so the average opacity basically, but he really predicted also, he calibrated individual lines here. So if you look at these opacities, they all have individual lines. Each line represents a different transition from some higher energy level to the lower energy level basically. And he calibrated these with experimental data. And this is very important if you want to analyze and identify the individual lines in an observed spectrum, and you want to associate this with specific elements. So this was done by Andreas Fleurs recently in a study. But these plots here, they are shown from a different study, from an older study. Then let me also mention something else connected to neutron-star mergers. That is not really the kilonova part, but the gravitational wave emission. During the merger, you have different phases of gravitational wave emission. This in-spiral phase, this is basically when the two neutron stars revolve around each other. They are very compact, very massive, very close to each other. They are strong emitters of gravitational wave here, and they come closer and closer. The reason why they come closer is simply because they emit gravitational waves and lose energy and angular momentum. Otherwise, they would just revolve around each other at the same stable orbit for an infinite amount of time. But they emit gravitational waves, and that is the reason they actually merge at some point with each other. And this merging process takes place on milliseconds here. And in the in-spiral is basically characterized with a relatively simple behavior. You have an increasing amplitude here, increasing frequency also, but at some point the signal becomes very complicated, and this is really where you need hydrodynamical simulations also to predict this gravitational wave signal. So from here, starting from here on, this is basically the point where the two neutron stars touch and then eventually merge with each other. This is called then the post-merger phase here, and this can go on for several tens of milliseconds to seconds and longer, but with a declining amplitude, of course. And so there are two things to say here about this, namely this part here of the signal is easier to observe. And this was observed also in GW17, which I will come to in a second also, in this observed neutron-star merger event. And it provides some information, it provides crucial information about the masses of the two neutron stars here, this in-spiral signal. And it also contains some information about the equation of state, the nuclear equation of state, which is still mysterious and one of the goals to learn about from these neutron-star mergers. And the post-merger signal is more difficult to observe because it has a higher frequency and lower amplitude. But if we could see this at some point, this was not observed in GW17, but if at some point we could see this, we would gain a lot of information about the equation of state here from this post-merger signal. Right, and then one other messenger here of this multi-messenger events of neutron-star mergers is, of course, gamma ray bursts. I will not say a lot here to this. There are basically two classes of observed gamma ray bursts, and both of them are still somewhat mysterious. We have the main idea or the main candidates for these long gamma ray bursts that are longer than 2 seconds are massive stars. And short gamma ray bursts, people have advocated gamma ray bursts for a long time, and this seems to be still valid, this picture. However, there are still questions about how many of the long bursts can actually be caused by gamma ray bursts. There are indications that some long bursts are also caused by neutron-star mergers, excuse me. But they're also indicating that short bursts can be produced by by massive stars. And what is the scenario? How can they be produced? There are two possible scenarios. Basically, it can happen if you have in the center sitting a neutron star, a strongly rotating neutron star with a strong magnetic field. This is believed to create some jet-like outflow here along the rotation axis. Or if this thing collapses here, the central neutron star collapses and forms a black hole, then you could also create some jet-like ultra-relativistic outflow here along the rotation axis from this black hole accretion disk here. So these are just artistic expressions, artistic impressions shown here. They are not really pictures from simulations, just shown for you to get an idea, basically. And one other important aspect here that I mentioned already is what can we learn about the equation of state. And there is one important thing to realize, namely, if one can associate a given equation of state, which is plotted here exemplarily for different models, different equation of state models, pressure versus density here, equations of state models are plotted on the left. One can associate these with mass and radius relationships of cold non-rotating neutron stars. So for a given mass of a neutron star and a given equation of state model, you can predict the radius then of a neutron star. And so these relationships here are basically, you can calculate this with the Tolman-Oppenheimer-Volkoff, the TOF equations. And so that means that basically if you know properties of a cold neutron star, then you also will know something about the nuclear equation of state. But so in the context of neutron star mergers, there's one additional tendency that one can say is roughly valid. Namely, if you have a softer or stiffer equation of state, soft in this case means a smaller neutron star radius, so lower pressure for a given density, then you will then your remnant of a neutron star merger will not survive as long as a neutron star, but will collapse earlier to a black hole. And this remnant is often called a hypermassive neutron star, so sometimes abbreviated with HMNS. Right. So okay, then I mentioned it already. There was one event, the GW17. You probably have heard of it. It's already now 9 years, but people still say it was recent. So it was this famous event so far, still the only event really that gave us all this nice signals here. So this really gave us an inspiral gravitational wave signal, a gamma ray burst, and kilonova spectra and a kilonova light curve. And the light curve indeed was characterized by this T2-1.3 behavior here, strongly suggesting that this was really an R process going on in the ejected material. So this was really nice. Basically a confirmation that the neutron star mergers are really R process sites. However, there are still many questions open. And in fact, several questions have opened up due to GW17 that were not present before. Basically making it clear to us, to the community, that we still haven't understood many things. So the mass and the composition in this observed event is still unclear, even after the many works looking into this. We also don't know yet the relevant nuclear reactions going on in there. So the abundance pattern really is unclear. We also don't know the time when a black hole was formed in this event. We actually cannot really say for sure if a black hole was formed. We think it was, but it is not 100% sure. And we also don't really know or we also don't have really safe or constraining information about the nuclear equation of state. We have some constraining information, but it would be nicer. We could get more constraining information if we would understand the event better. And this is basically our work tasks, our tasks of work to work on these aspects. So I mentioned it already. Here I sketched the evolutionary pathways of a neutron-star merger. I mentioned already that there are two outcomes of a neutron-star merger. Either you can create a black hole immediately. This is called the prompt collapse scenario. But you can also, if the equation of state is stiff and you have a low mass neutron-star binary, then you can create some intermediate phase here, namely a strongly rotating massive neutron star, which can collapse at some point later. Also, it might be indefinitely stable if the neutron stars are very low mass. But in the typical scenario, typical neutron star, assuming that it is 1.3 solar mass or so, then the typical scenario is that this will collapse at some point, and the ejected material will undergo nucleosynthesis and will shine in a kilonova. And for modelers like me, what are the main challenges? I will not go through each of these. Basically, just summarize the main fields. So the main difficulty is the main three difficulties are neutrino transport, which is very computationally expansive, because in principle it would require 6-dimensional Boltzmann transport to be performed, which is much more costly than just 3D hydrodynamics. Magnetic fields are very challenging because magnetic fields require a very high resolution, a very fine resolution, making the simulations very time demanding. And also the general relativistic effects are also challenging, because one really needs to solve essentially the metric equations for the metric of this for the GR metric around this merger, which is also not trivial and computationally challenging. So now I will go into what we have worked on recently here. And summarize these end-to-end models we have called for the kilonova of models with a delayed black hole formation. So scenarios where you do not create the black hole promptly, but after some while. So basically what we do is we simulate the merger with one simulation tool. These are simulations happen that cover roughly tens of milliseconds of evolution. Then we map this configuration to another simulation code specifically designed for evolving this post-merger system. Then the output of these simulations we plug into nucleosynthesis calculations. So the output we extract in the form of trajectories of individual outflow particles and give this to our collaborators who are nuclear physics experts to perform the nucleosynthesis calculations for each trajectory, and then they calculate the abundances. And then other collaborators of us are experts on kilonova radiative transfer. They then take the final results for the ejected material and the nucleosynthesis yields, plug this into their radiative transfer codes, and calculate predictions for the kilonova signal. And basically the idea is then there's a backward inference idea here that we for an observed kilonova, for example, for GW17, but also for future ones, we want to really learn something about these other ingredients, these other pillars of modeling here from an observations of a kilonova. Here I just flash the tools that we are using, but I will not go into details here because this is too time consuming. So now I will show some movies for you to get an idea what is happening. So here you see a simulation of a neutron-star merger performed here at GSI. And this is a rendering where you see isodensity contours. This does not directly show you the ejected material, but you can imagine. So these are density contours of 10 to 11, 10 to 12, 13, 14, 15, and so on. So you have very dense hypermassive neutron star being formed here in this simulation. And during this phase already, you create some amount of ejected material, which is called then the dynamical ejector. It's the early part of the ejected material, and this already leads to the ejection of 10 to minus 3 solar mass, roughly. And then if you continue the evolution, now we switch the perspective. The rotation axis is now here. And we look into the poloidal plane here. On the right, you see this YE quantity, the electron fraction. On the left, the density. And we evolve this now starting from 10 millisecond after merger and continue now to 100 millisecond. And you see that the YE will change somewhat here. The YE will increase to 0.5 in the polar regions close to this rotation axis, while it will remain low in these equatorial regions here. And so this this can be all explained with the mechanisms related to neutrino transport. I will not go into the details here. Only say that basically this material here on the poles is coming from the so-called neutrino-driven wind, which comes from neutrino absorption. Neutrinos are emitted from the center, absorbed in the outer layers, and this absorption causes heating, and the heating then causes PDV expansion, so thermal expansion of these polar layers, and this leads to expansion of this neutrino-driven wind, and it's because of the absorption of many neutrinos here. This YE is typically very high, close to 0.5, so not a good candidate. So this component here, this polar component, is not a good candidate for our process nucleosynthesis. But the equatorial components here are more favorable for our process nucleosynthesis, and these are mainly driven by viscous winds. But I will not go further into detail because I don't have too much time. And then, so at this 160 millisecond, what happened here is basically that the central neutron star became unstable to gravitation. It collapsed to a black hole. This collapse we describe with our simulations in an approximate manner, not fully GR, but in an approximate GR manner. We describe this in our simulation. And then we continue the simulation with this black hole accretion torus. And then also during the evolution of the black hole accretion torus, we obtain more ejected material here from this accretion torus, typically not so fast, but relatively neutron rich. And that means we have basically three main components of a neutron star merger. One component is this dynamical ejector. This is the fastest ejector. This is basically here on the outer parts of the ejected material and with the highest velocities. Then we have the material ejected during the neutron star torus evolution. And then we also have this ejector from the black hole torus evolution. And now we can look into what material, what elements are produced from these ejection components, ejector components, and also look at the YE distribution here. And we see already that the dynamical ejector have the lowest YE, and therefore, not surprisingly, the lowest YE means the highest neutron densities. They create the heaviest elements here. If we look at the abundance pattern here, and the dots, the circles here in the back are the solar abundance pattern. So, and the comparison with the solar then indicates already, okay, these neutron-star merger systems that we simulated here can produce already relatively fairly well this solar distribution, not perfectly, but fairly well. So they recreate this first peak, second peak, third peak, but in the heavier part, they are a bit deficient here. So this is something that I will come to in a minute, how one can get this also in neutron-star mergers. But these models did not produce it. But now looking at the kilonova light curve, this is basically the emitted light versus time. We predicted from our models the light curve here. These are these lines, and the observed light curve seen in GW17 are these circles here. And this plot basically indicates that our models are fairly well in the ballpark, at least, of this observed event. And now, if we would have taken only the dynamical ejector material and calculated the kilonova light curve for just this dynamical ejector, we would have gotten something like this here. And this means that this indicates that taking or simulating only the early part of the merger, where you create this dynamical ejector, is insufficient, will not give you massive or sufficiently massive ejector to obtain high luminosities that you need for this observed event. So the observed event, GW17, was probably dominated by not the dynamical ejector, but by the post-merger ejector, so by neutron-star torus and black hole torus ejector. And this highlights basically the importance of simulating a neutron-star merger for a long time, so that you really see so that you really predict also the properties of the post-merger ejector. And our collaborators in Belfast, they used another more sophisticated Monte Carlo transfer scheme. This is called ARTIS. It was often used also for type 1a supernovae. Then they have adapted this code for kilonovae as well, and looked into the spectra here, so not the light as function of time, but for a given time, the spectrum, so the light, the emitted light versus frequency or wavelength in this case here. And so this gray line here is the observed event, and this was our model. And one nice feature here of our model was that it really reproduces this bump that we see here around 8,000 angstrom. And this dip here. And this dip is believed to be associated with strontium. And strontium is the first peak R process element. And so far, really, this strontium is the best explanation for this bump here, for this dip. And this means basically that we have more or less safe confirmation that we really have had R process nucleosynthesis going on in the ejector here. Right. And one other aspect that is very interesting, that is very fashionable right now in this business of neutron-star merger modeling is also neutrino flavor conversions. The models that I have shown, they did not include any of this neutrino flavor conversions, but it's been clear by now that potentially they play a significant role, these flavor conversions. As you know, neutrinos are known to have a finite mass, so they are not really massless, and because they have a finite mass, their flavors can oscillate. So they can oscillate between electron, muon, and tau flavors. And this can happen on very short time scales and very short length scales. And in fact, there was a discovery of a flavor instability called the fast flavor instability several years ago. That there it was realized that this can really happen on timescales of nanoseconds here and on length scales of centimeters. And this is way too short for us modelers, for us hydromodelers, to include this into simulations globally. But we have found some way of including it approximately. And this we have done with one of these neutron-star merger models here, where we have just used some simple scheme of mixing these flavors, basically, assuming some very simple mixing prescription here, but we have played around with different mixing prescriptions, and it turned out that the abundance pattern that we get here for one of these models showed that we can get abundance closer to solar, so more neutron-rich conditions basically in the ejector, and this could be one of the explanations basically how one can get a closer to solar distribution here in these models. So basically, this just illustrates that more work is needed, and it's very promising, this flavor conversion analysis, and more work in this direction is needed in the future. But then I would also like to briefly discuss another work that we have done on the lifetime of the remnant in GW17. So in GW17, this observed event, the lifetime of the neutron star, of this hypermassive neutron star, which is called tau black hole, so the black hole formation time here, this is quite uncertain in this event. It is relatively clear that we had a delayed collapse, so probably most likely we did not have a prompt collapse, because if we had a prompt collapse, then the ejector mass would not have been so high, but the ejector mass must have been high because we have seen a very bright kilonova. And therefore, we can more or less exclude that we had a prompt collapse. However, we don't know the upper limit for this lifetime. We don't really know for certain that that the remnant collapsed so far, but we have some ideas at least. So there is the idea, if, for example, if the gamma ray burst was really coming from a black hole torus system, which is speculated by many people that it came from a black hole torus system, then the time between the gravitational wave signal and the gamma ray burst gives you an upper limit on the black hole formation time, and this was roughly 1.7 seconds in GW17. However, any time between that, between this here, 10 milliseconds roughly, and 1.7 seconds, this lifetime is completely unclear right now, and no model so far could really constrain that. And then this was basically the task of this project here, was to find if we could see signatures in the kilonova that could help us understand or constrain this lifetime better. And now, in order for you to understand this line of arguments that we had here, I want to show you two simulations. On the left, you see a simulation of a long-lived hypermassive neutron star. In this case, the collapse happens at roughly 200 milliseconds. And on the right, you see a short-lived hypermassive neutron star scenario. And on top, you see just the center, and on the bottom, you see the ejected material zooming out, basically. So the picture zooms out, and you see all of the ejected material. And the main difference you can see already here on the bottom panels is that you create a large bubble of high YE in this long-lived scenario, which is much smaller in the short-lived scenario. And this is because the hypermassive neutron star, as I mentioned already, it creates this neutrino-driven wind during its lifetime. And this is the reason for this high YE bubble here, basically. So then basically using this here and seeing this, one naturally asks the question, okay, what is the signature of the kilonova and of this high YE bubble? And in order to address this, one first looks at the abundance of this high YE bubble. So here are histograms in entropy and YE space, and basically this high YE bubble is in this region here. For a long-lived scenario, it's here. So basically the question is, what elements are produced in this region, for this material here? And turns out that this is mainly helium and iron group nuclei. And right, and so here we also see an abundance pattern. And here also what I wanted to mention, actually, here a short-lived neutron star merger also produces a abundance pattern much closer to a solar system, to the solar system abundances here. So this is also one possibility how one could better explain the solar abundances here with the short-lived scenario. But for the point now was to look at this high YE signature here. And so it's basically helium. And now one can look at the production of helium as a function of time after merger for different scenarios, for different models. Here, all these models are characterized by different lifetimes of the neutron star or black hole formation times. So all these dots are the times of black hole formation. And you basically see that the longer the neutron star lives, the more helium is produced in these events. So now the question is, could we find an observational signature of this helium? And it turned out that this dip that I have mentioned here, which at early times is believed to be associated with strontium, at later times, so this is a picture at 4.4 days here, the spectrum at 4.4 days after the merger. At later times, it turns out that this can be used as to find an upper limit on the amount of helium that is produced there. Because if more helium would have been created in this event, we would have expected a deeper and deeper dip here in this spectrum, which we have not seen. We only have seen a dip like this here. And so this was the observed signal. That means we can place an upper limit on the helium fraction in this observed event. And this is very nice. So this means basically, if we connect these two plots here, basically, we can infer an upper limit on the lifetime of GW17, of the lifetime of the neutron star, which in our case was roughly 20 to 30 milliseconds here. And so this we can then connect also to other things, to the equation of state. I will jump over it because I'm a bit short on time now. And how this can be done, these are more technical aspects here. But basically what this allowed us then to do is to place constraints on the equation of state. So now here are plots again for this mass radius relationships of equations of neutron stars. So each line represents an equation of state model, a different equation of state model. And basically our constraint of the low helium mass fraction excludes all these red lines here. So all the red equation of states models here are then excluded by our new constraint here, which is quite interesting for nuclear physicists. However, I have to say that at this point there are still uncertainties in this modeling here, and it's not 100% safe. But the idea is new. It's a new and potentially quite powerful equation of state constraint, and future more dedicated studies then will explore deeper the boundaries of this constraint here. Right, and I think I'm a bit short on time. I should probably stop soon, right? What is the time limit?
No, please go ahead. We have time.
There would be maybe one more topic, one more paper that I would like to discuss. Is this Rhine paper? We are calling it so. Rhine is a new scheme that we have developed recently. And that stands for R-process heating implementation hydrodynamic simulation with neural networks. So we are using these, we are basically, the main motivation of this is that we want to implement this heating at early times. This heating rate I have already shown in the beginning, this heating because of R-process nucleosynthesis. We want to implement this heating at early times in hydrodynamic simulations. So far, basically, almost all of the models, by now there are some more models who implement that already approximately, but 99%, let's say, of existing hydrodynamic simulations, they neglect this dynamical input of this early heating. So basically, the heating of R-process, due to R-process nucleosynthesis and decay, produces on the order of 2 to 3 or 4 MeV per nucleon. And that is quite substantial. That if you look on the effect here, or if you convert that roughly to velocities, you would expect a boost of 0.1 c roughly, so 10% the speed of light corresponds to this 3 MeV roughly. And so this means that one should include it because it can be dynamically important, this heating. But because our process nucleosynthesis is so vastly complex, because you need to advect and describe nuclear reactions for thousands of isotopes, which cannot be done in a multi-dimensional hydrodynamic simulation. It's too expensive, basically. Therefore, it has not been, it's not implemented yet, but you would like to include that. And one way of including this is to do that with training neural networks, using trajectories of nucleosynthesis calculations, of detailed nucleosynthesis calculations, and using then these neural networks to describe source terms for individual advection equations of individual species by these and describe these source terms with these neural networks. So basically what we do is we advect a few more species in our hydrodynamical simulations, neutrons, protons, alphas, and subsumed heavy nuclei fraction. So XH is basically all heavy nuclei, all nuclei heavier than helium, and subsumed into one species. And we advect this with one equation each here, these quantities. And we also advect the mass number of heavy nuclei. And then we have basically 5 additional advection equations. And for these advection equations, we need source terms, basically. So we need terms that describe us the nuclear physics reactions going on at each time step and at each location, basically, during the simulation. And these source terms are then described by neural networks. And these neural networks are trained, basically, with detailed nucleosynthesis calculations. And so basically, we are using a black box, more or less, this Rhine scheme here. These are really just neural networks that do this forward inference here of these trained neural networks, and they give us then these source terms during the evolution. And what does it do? So now here I compare two simulations on the left without Rhine and on the right with Rhine of a neutron-star merger. And so this is again the phase right after the neutron-star merger, where you still have the hypermassive neutron star. Around 200 milliseconds after merger, this will collapse. And at early times, you don't see much because our process happens on a time scale of 1 second, roughly. So you will start to see effects after 1 second, roughly. And so what you expect basically is that material is accelerated at velocities of the displayed region here. So you will now see that the ejected material here, this outflow material, is accelerated, is a bit faster, and it's also more fluffy. So basically, the energy deposition creates heat, and the heat causes material to expand in all directions. And this means that basically you erase substructures in the ejected material and create a more spherical outflow here, compared to the case without heating. And also, you can also see that the electron fraction is higher here than here, because what we also describe with Rhine is the increase of the electron fraction, because beta decay, after the R process, you have beta decay, you have radioactive decay towards the line of stability, and this beta decay increases YE, and we describe this YE increase through beta decay. We also describe with this Rhine scheme, and that is the reason why you also see this high YE here at later times. Right. One other thing that we looked at is the nucleosynthesis yields. for these Rhine models, but it turned out that actually a little bit unfortunate that it didn't have much effect on the nucleosynthesis. So lots of effort we put in, but it turned out that the effect on the nucleosynthesis was not so large. So purple lines are with this Rhine scheme and black lines are without, and you can hardly distinguish the abundances here. But as I've mentioned already, we definitely saw an impact on the velocity distribution. So the velocity of the ejecta was boosted significantly compared to the case without Rhine, but not the abundance. Yeah. So, but because the velocity was boosted, we also saw quite some effect on the kilonova light curve. So basically, the light curve is boosted because you expand material faster, and this means that photons can be released faster from the outflow, and the light is then is more, the kilonova is more luminous, so more emission comes out from this ejecta, right? And I think I will skip this because I'm a bit I'm speaking already quite long. So these were aspects more to the gamma ray burst, and collapse I actually didn't want to speak about. And now I will summarize. So as I hope to make clear is that neutron-star mergers are definitely promising site for R-process nucleosynthesis, and so far they are the only confirmed site. But there are other candidates as well. So whether they are the main sites is still an open question. We don't know, but they are definitely sites of R-process nucleosynthesis. And the kilonova, that is the electromagnetic emission from this system, contains valuable information about the produced elements. Not only the light curve, but also the spectrum. And there are, we have one of our main lines of work in the last 1 or 2 years has been this looking at the constraint on the equation of state that we could get from the kilonova. And there we have found that the neutrino-driven wind that creates helium can give a signature that would be identifiable in the spectrum of the kilonova. And applied to GW17, we infer from this signature that probably we have seen a short-lived scenario where the neutron star has collapsed already after 20 to 30 milliseconds. And this would translate then also, this also has important implications for the equation of state. Also, what I've briefly shown was this Rhine scheme for the R-process heating, which uses neural networks, so machine learning basically to implement, to mimic source terms. This was a quite nice tool, but it turned out that the impact on the nucleosynthesis was not that large, but the effect on the kilonova was quite substantial. And then also what I've skipped, just mentioning briefly, I want to mention briefly, there are also other efforts going on with identifying emission from the late kilonova. And there we have emission features, and if we believe that certain bumps in this emission feature come from certain elements, then we can place also interesting constraints on the nucleosynthesis. And with that, I would like to stop here, and thank you for your attention. Thank you very much.
So many thanks for the very interesting, very informative talk. There is time for questions. First from people in the audience here.
So
speak loud so that you can hear.
Can you explain again how from the helium signature you went to equation of state constraints?
Yes, sure. Go back. So, this is a chain of arguments. So we first place an upper limit on the helium. There we find in roughly that the helium mass fraction cannot be greater than 5% roughly. Using this left plot here, basically, we get a limit then on the lifetime of the neutron star. So then if we want to get a constraint on the equation of state, we need to translate this lifetime limit into a limit for the threshold mass. So what is the threshold mass? The threshold mass is indicated here in this slide. For high total mass, so M1, M2 are the masses of the two neutron stars here. And if the total mass is large, then you would get a prompt collapse. If it is not so large, then you would get a delayed collapse. That means that if you plot the lifetime or the black hole formation time as function of m tot, you would get a line that looks like this roughly. Yeah. And here you have one distinguished point here. This is the threshold mass. This is basically the total mass at which you would get a prompt collapse. Yeah, so below this mass, you would get delayed collapse. Above this mass, you would get a prompt collapse. And this is one, for a given equation of state, this is a given value, basically, for a symmetric merger with non-spinning neutron stars. Yeah. So that means that one can correlate. So sorry, let me skip this here. So one can correlate then the threshold mass with properties of the neutron star, or with equation of state properties. And so here this basically illustrates how we get a constraint from how we translate the constraint from the lifetime to a constraint on the threshold mass. And now if we have a constraint of the threshold mass, we use this relation here. This is an empirical relation, has been found by performing many simulations of neutron star mergers. And max here is the maximum mass for a given equation of state, the maximum mass where a non-rotating neutron star is still stable, maximum TOF mass here. And R is the radius, Q is the mass ratio. And these are basically coefficients here that have been determined from fitting. So this is basically an empirical relation, a fit relation between the threshold mass and these two quantities, M max and R. Oh, three quantities, including Q. Yeah. And I don't have this slide here where, yeah, basically this means then if we have a boundary, if we have bounds on this threshold mass, so the lower bound of the threshold mass was exactly 2.75 or so, the total mass of GW17, that was 2.75 solar mass or something. And we know that it cannot have been larger than 0.2 solar mass or so higher than this 2.75. That means that we have a bound of the threshold mass between 2.75 and 2.95. And this then allows us to infer exclusion regions basically in this plane of M max and radius. I don't show it. Here it's shown. Here it's shown. So this is basically the plane showing M max and radius. And we have through this equation here, if we have a bound on the left side, we get an exclusion region on the quantities on the right side, basically. And this is this exclusion region here. The other two exclusion regions that are shown here, so this is here basically another constraint. This is not the helium constraint. This is a constraint that we have not seen a prompt collapse, which is essentially excluded by the large ejector masses and the bright kilonova. And this is another constraint. This basically means here that we cannot have equations of state with a speed of sound larger than the speed of light, basically. Yeah. This means causality in this case. And this means that we end up with this viability region here if we use these three exclusion regions. Did that answer the question?
Okay. So other questions, please?
Why do you think that the process heating doesn't have such an impact on the nucleosynthesis?
Sorry, could you repeat? I just understood R process, nucleosynthesis, and heating.
Do you think the R process heating doesn't have such an impact on nucleosynthesis in your latest work?
Yeah, this is, it's actually not too surprising, honestly, because the R process heating, as I mentioned already, it takes place on relatively long timescales of 1 second or so. Basically, R process heating sets in when you already have created all the unstable nuclei during the R process. So first you have the R process along the drip line and going up to heavy elements, far away from valley of stability. And then all these R process nuclei decay back to the valley of stability. And you only get the majority of heating energy during the decay. So first you have the actual R process and then the decay. And the energy input, the energy release happens mainly during the decay. That is already basically after the actual R process. And mainly that's the main reason why we don't get a big impact on the R process nucleosynthesis itself. No.
More questions? Anyone from our friends that are online? Any question? I don't see any raised hand or. Okay. Okay, then many thanks again for the talk.
Sure, it was a pleasure. Yeah, thanks to you. Yeah, for inviting me.
Thank you for having you with us. And the talk will be available maybe even already today for those who want to follow it again. So okay. So thank you.
Yeah.
Bye.
Thank you. See you.
See you.
Bye-bye. Bye-bye.
En met de vorige dag